Good morning, everybody. Today, I am Shatak Singhal, and today I'll be teaching you mathematics and other engineering type courses. And let us start off first of all with the first chapter itself, Relations and Functions, Part 1. And today, we'll be focusing much on the basics of mathematics and build on those concepts so that we can ease our learning and better understand other complicated concepts in the future. So let us start. First, what are relations and functions? We'll come to that, but first let's start with the most fun part, a limerick and a goal to understand before we start our first class. So, our goal is to understand relation and function and understand the basic mathematics for calculus, linear algebra for infinite and finite dimensional analysis. No need to worry about that. We'll go to it further on. But for now, let's enjoy the limerick which I just made. There once was a relation so wide when many appear side by side. When each input chose just one output it knows, then a function it proudly supplied. This is a definition of a function. I will come to that later during this video. But first, let us start off. What are classifications of real numbers? What are real numbers in the first place? And how we can include numbers in mathematics? Well, we already know how to include numbers in mathematics, but how to include many other concepts which we don't know about till now in mathematics. So let me introduce you to natural numbers, which are numbers which do not have any decimal places, but range from 1 to infinity, which means it can be 1, 2, 3, 4, 5, 6, 7, 8 to infinity. And it will go in this order. Whole numbers are like natural numbers only, but they only include one number, and that's 0. Like in natural numbers, we did include a 0. We started off with 1. In whole numbers, we start off with 0 and then to infinity. And it goes with the same logic 0, 1, 2, 3, 4, 5, 6 to infinity. Now, let's go for integers. Now, let us be a bit negative about this. We have negative numbers being included in our consideration. Earlier we used to have positive numbers from 0 to infinite numbers, but now we also include the negative aspects of these numbers, their evil parts, which we haven't known about till now. And those are integers. We have minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7. We have 1, 2, 3, 4, 5, 6. We include both positive and negative parts for that particular number. Now, let's go for rational numbers. Rational numbers include decimal places now, but they also include integers too. They also include the negative parts of those decimal values. For example, like we have 51.6549. Or over here, I have given some examples like 3.2567. We can also have its negative part, minus 3.2567. But we'll come into much more detail in a few minutes. Now we have irrational numbers that are similar to rational numbers. For now, let's think of them to be similar, and I'll later on explain that they're completely different things. And real numbers is everything. Natural numbers, whole numbers, integers, rationals, irrational numbers, everything we have learned till now, all combined together will form real numbers, a group of real numbers. Now, let us find a difference between these rational and irrational numbers. Now, one thing we need to know about the difference between a rational number and an irrational number is that one thing we need to know is rational numbers are of two types, but irrational, unlike rational, plays our game a bit differently in mathematics. For example, give me a number 1.235. Okay, that sounds logical, I guess. And let's take it as 1.235 bar. Now, 1.235 is just a normal number, right? But when we go to 1.235 bar, what does that bar represent? Well, it is equal to 1.235, 235, 235, and it goes on. Huh. Same repeating decimal positions, but just repeating onwards. Same numerical value repeating onwards, like 235, 235, 235, and it never stops. These are known as repeating rational numbers. The first one is actually a finite rational number. Well, we don't call it as finite and repeating rational numbers. That's how I remember my stuff in a more casual manner. But over here, 1.235 is considered to be a rational number because it has finite decimal places. But shouldn't it not go for the second one? Well, if they if the number is being repeated after decimal places and there are patterns in it, for example, 235 is being repeated all the time. That's the only pattern you have to remember. If any number after decimal is repeating itself many times, then it is considered as a rational number. But it will be considered as like a repeating rational number, but it is considered under rational numbers. Whereas we have heard about pie, and I'm not talking about apple pie, even though that's the favorite kind of pie, or not even about magpies. We're not talking about any kind of pies over here, only about a mathematical pie, which is somewhere about 3.14, and you don't need to know the rest of the numbers. There's like a bunch of numbers, and it somehow goes till 5, 4, and it continues. Well, my last digits might be wrong, but what I actually want to show you here is that over here, the same number isn't repeating in the end. It's just a random bunch of numbers after the decimal position. And we don't know whether there's a pattern to it or whether there's any repetition of the same numbers repeatedly. And this is where irrational comes into consideration. When you have an infinite amount of numbers, but there are no repetitions in it, like there's no bars upon it. This is a much more intuitive way of understanding it. So, the difference between a rational and an irrational is that rational has two types: finite numbers and also infinite, but they're repeating. But in irrational, you have infinite, but they're non repeating. Now, this makes sense. Now, we will learn more about this circle in a few minutes and what they actually represent. And they will help us understand how we group everything in mathematics. Now, let's first focus on mathematical machines, or in my words, boxes. For example, we have cooking, for example. We put, if you want to bake a cake in Minecraft, you gotta put flour, eggs, and wheat into the mixture, and then you get the cake as an output. But what makes that cake is an arrow. Well, that's what you see in Minecraft, of course. And over here, I'm showing the exact same thing. If we put an input into a machine, we get an output for that machine itself. For example, as I said in cooking, if you put something inside of something and let that machine process on that ingredients, then it will give you a cake. So over here, what I'm trying to say, if I put this one, a value inside the machine one, it will give me the output for the machine as 3. So imagine 1 to be eggs, flours and everything, and 3 to be the cake. And the machine is like an oven that processes on it, or a food processor, as per se. The technology we don't have until now, and we would love to have it. 3 acts as an input for machine 2, and 4 is the output for machine 2. But what I'm trying to say over here, is that machines take in inputs and give you outputs, and these mathematical machines are called as functions due to their well-defined rules, which we will see in the upcoming slides. So this is what I want to make you visualize. Inputs go in, the machine works on it and gives us an output, just like a computer monitor. So inputs can be considered as a variable x, machine can be written as a function f, and f works on x to create f of x. This is the mathematical form of it, and we will get more deep into this right now in a few minutes. Now, let us talk about this diagram. Now, this is known as a Venn diagram, and over here we have an input space and an output space. We'll explain what these spaces are later on and how they help in grouping. But what you all need to know is that this input space is nothing but the input of the machine, and this one on the right hand side is actually the output of the machine. And these lines which you see over here are actually the function, but right now we'll consider them as relation line because I have to explain you the difference between a relation and a function, which is the main part of this chapter. So here is the difference between a function and a relation. Let's get into it, shall we? A relation may or may not be a function. Well, it's obvious, Sherlock. Now, what a function is all functions are relations. Okay, how? We'll see to it. Relation may relate one member of the domain to more than one member of the range, while a function relates each member of the domain to one and only one member of the range. For given x, there's only one and only one y. Example, as you can see over here, 2 relates to 4 and 6, but 4 relates to 9 and 8 relates to 12. But when you see the function over here in the right hand side, what you see that each input is giving you a unique output, and this is what you call a function. But we'll get into the rules of a function later on, and for now let us look through these examples. Let us start with the functions. Now let us go to the first example. 1 is connected to 6, 2 is connected to 10, 3 is connected to 8, 4 is connected to 9, and 5 is connected to 7. This is particularly different from what we have seen in the example, but in reality they are the same, no matter how jumbled these lines are. It's a visual representation to see how they are connected, but they all are uniquely connected to each other. Each input has a unique output. So this is a function. Now, let us go to the second example, shall we? 1 is connected to both 9 and 10, which is a bit odd, but we'll come to that later. But when you see the other numbers 2, 3, 4, and 5, they're uniquely connected to 6, 7, 8, and 9. But let's come back to the power of 1. Can 1 be connected to both 9 and 10? Can one input give you two outputs? The answer is no. One input cannot give you two or more outputs, and so it wouldn't be considered as a function but a relation. Now let us go for this example. Example number 3. 1 is connected to 8, 2 is connected to 9, 3 is connected to 10, 4 is connected to 10, and 5 is connected to 7. Okay, over here we have found two odd things. First of all, 3 and 4 are connected to 10. And 6 doesn't have any inputs. Can it be possible that two inputs can give you one similar output? Yes, that is possible. But in this case, this is not a function. And the reason why that is that 6 doesn't have an input. Because each output should have an input, no matter what the cost. Each output should have an input. There can never be a case where there is an output but there is no input that has any relation with that output. Slow down the video and rethink of what I said again. and then you'll be much more clear with the concept. So this is a relation, and not because of the fact that there is 3 and 4 connected to a similar output, but it's because that 6 doesn't have an input. Example 4 goes a bit more deeper into the 3 and 4 conclusion. Now, 1 is connected to 6, 2 is connected to 7, 3 is connected to 8, 4 is connected to 10, 5 is connected to 10, but 0 is connected to 9. Each output has been connected to an input, but 4 and 5 give you a similar output 10. Do you know what this means? As I said earlier, this is a function. Due to what reason? The reason is that over here, according to the definition which I'll tell you in a few moments, you'll see that everything in mathematics follows definition. Once you know the definition itself, you can get a proper understanding on how we differentiate things and how we work with different kinds of complex mathematics. So basically, mathematics is on a basic set of rules for us to ease our understanding about different types of structures in mathematics. So I will get into that in a few minutes. And this is a function. Last and not the least example, 1 is connected to 6, 2 connected to 1, 3 is connected to 7, 4 is connected to 6. But 5 being the input isn't connected to any output. And the thing is, it's reasonable too. Look, the thing is, you can have no output without an input. For example, you can't just have some cake without putting any ingredients within it. But if you have any ingredients within it, you don't need to process it. If you have a processor and it's broken down, then it won't give you any output. So if you see, having an input but having no output makes sense, but having an output given that there is no input for it, that doesn't make sense. So 5 is considered as a function also. Basically, maths is about real life logic, and once you understand that logic, it becomes much more easier. Now, these are the rules for the functions. The input can have no more than one output, or each input can have no more than one output. So what this means is that if you have one input, it can only give you either one output or no outputs. That's are the only two cases we have. And second rule is that each output can have at least one input. This at least word means it can be any number from 1 and above 1. It can be 2, 3, 4 to infinity. But in the input case, it can have only 0 and 1. So an input can have no output or can have one output. But an output can have at least one input. As I said, you have different things for making a cake and you get one thing out of it, and that is cake. But for an input, if you're not giving anything to the processor, how will you get anything out of it? If that makes sense. So this is all about the differentiation between a function and a relation. And we'll come up in a few minutes why this image, which I've shown in the starting, makes sense by giving you an example. Now, let's learn about space. I'm not talking about stars or galaxies. I'm more oftenly talking about the mathematical world that we live in. Space is like a normal space but in a mathematical form, and I showed you the transformation over here, which I got from Google. Now we have learned about 3D space, 2D space in our high school, and this is a concrete way of understanding spaces. And they can be more spaces when we go into more abstract mathematics, like 4D, 5D, 6D to infinity. But we won't get into that right now. We'll learn much more amazing stuff in the future classes. But for now, what you need to know, place where mathematical objects are represented is space in mathematics. Now, what are objects? When I say objects, I do not mean tables and chairs or the laptop I'm right now sitting on. I'm talking about numbers. Yes, everything comes down to numbers, but there's more to numbers than we know about for now. We also include variables in our spaces. For example, an object can be anything. A number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2.5, and 6.767 something, and that's intentional, but you get the point. Or it can be a variable. Variables like x, y, z, w, abc, dollar sign, this sign, whatever. Anything that you can equate to. Now, we also have sets. We have close bracket sets 1, 2, 3, 4. We also have open bracket sets 2, comma 3, comma 4. And we also have these kinds of sets. Or we have these kinds of sets. And we also have these kinds of sets. And last and not the least, matrices, which we learn in linear algebra, which is kind of like sets, but we represent them as vectors and take a group of them, which we won't get into it right now. But for now, what you need to learn, object is like anything you can represent the real world in a more mathematical form. Like you can think of the space we live in as a 3D space, and the distance we walk as numbers, or the distance we walk. So, this is all about spaces. Now, let us get to domain, range, and codomain, which comes under the category of spaces. Well, I made them into category of spaces, so I can make it much more easier for you to understand. What is a domain? Well, as I've said earlier, when I've been showing you this space, the input space is also known as the domain, and the output space is actually referred to as the range. But hey, listen, what is a codomain? Now, the codomain is the space we're actually considering. So, when we talk about spaces, we look at the observer perspective and a function perspective. Think it of as like you're looking at a bigger world, and then the function only acts in a smaller world, smaller part of that world. Now we'll come back to the part I was talking about earlier about circles. Remember when I was talking about these circles over here? Well, these circles actually represent a space in mathematics. Well, not the circles, you can create any object you want. But then the thing is, this is a way of representing on what is included in whom. For example, integers is like a smaller space than rational numbers because it groups a smaller part of number of that bigger group of rational numbers. Whole numbers only take in a smaller part of integers, but integers is also a part of a rational number. So whole numbers are also considered as rational numbers, but when we restrict the space or make it much more smaller to only include a finite number of objects or numbers. Same with natural numbers. But irrational numbers is a different case and it's not included to rational numbers, and that's separate. And they have no connection between them. Same with this. This is also a space. This is this is an input space, this is an output space. And as I've said already, this is the domain and this is the range. And the codomain is what we take as our space. And for example, we can do this question over here. So, as an observer, I take a huge consideration of a wider group of numbers. Let's not talk about spaces over here, but a group. Because a group is what a space is, almost. But here, for example, if I take a group of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I have a smaller space 9, 8, 3. You see, this space is already included within here. I can just make the circle around them. This space is already included over here. So this is a smaller space for it. And what I mean over here, I as an observer am choosing all these numbers, all this group of numbers, but the function, which is this, is only acting on these numbers. Now, we'll connect the topic in a few minutes, but let us first solve this question and get our understanding clear. If you understood this, you will understand what I'm gonna say next. So over here the question is, the function satisfies the codomain space where? Well, the English is a bit wrong over here, but what it's actually trying to say is that whether the range is equal to the codomain space, or whether the range is as big of a group as a codomain space. Here, in this case, it isn't. The range space is smaller than the codomain. Here it is, because it's equal. Over here, the codomain space doesn't satisfy the range space, and they both are not equal. So, therefore, only this case is satisfied, case 2. Now, thank you very much for looking at my YouTube video. But this is not the end. And if you want to like right now, share and subscribe, you can do. But for now, let us focus on the way of connecting all these topics which I just taught you right now. Now, we have learned about spaces, real numbers, and everything about functions. Now, the connection point is, we have these two circles over here, for example. As I said, this is the input space IS, and this is the output space OS. And if I put a random number over here, 1, 2, 3, 4, 5, this is 6, 7, 8, 9, 10. Now, in here what happens is that if this is considered a space or a domain, this is considered as a range, because this is where our function acts. But the range is where our function acts. That's which you have to remember. And the codomain is variable. It changes on the observation perspective or the observer's perspective. So if I have the codomain to be a bigger space of this, for example, 11, 12. So the function only acts like this. Now this is a function because it's uniquely identifiable, but over here in the other space, 11 and 12 is not included inside the range. But the space is there, it is present because we as an observer are looking at that space which has 11, 12, 6, 7, 8, 9, 10. But the range is a small space than this. So the range doesn't satisfy the codomain. That's alright, and we will look at how this property helps us in the future classes in calculus. But over here, these lines are uniquely identifiable to the range space, so the function acts over here. And we as an observer are looking at this whole space and just checking whether the function covers up the codomain space. That's all we're doing. And I want to also repeat myself that if you understood this way I'm using spaces over here, because the spaces over here are not these circles over here, it's just how we visualize a group of objects together. This is the connection point. And let us go back to the point I was gonna make till the end of the video, which I was saving for. Now, you have this domain and a range. Now, you might be wondering how a function is a subset of a relation, right? Now think about this, with all the rules we have followed till now. Let's have these infinite amount of numbers and it's going till infinity. We also have the same group over here. Now, let us say as our relation that every single number in the domain has a relation with every other number in the range. So 1 is connected to 1 is connected to 2, 1 is connected to 3, and all the infinite numbers. Same with 2. And this goes on, and it all gets very messy, and we don't want to get in that messy situation. Now, let's take our second example with a function. Now, this is our domain, and this is our range. Now, we have a number 1, 2, 3, 4, 5 to infinity. 1, 2, 3, 4, 5 to infinity. Now, the function is each number maps to itself, or maps in the sense it relates to itself. So it's like this. And it goes on and goes on to infinity. So you see, now the thing is, how many relations are there? Over here you have, now you can visually see that there are much more relations over here because one is connected to basically all the objects, and over here one is only connected to one of itself. So if you go for all the numbers, then there's so many relations over here than over here. And this says that the relation is actually bigger than the domain. So we have talked about two spaces today. One is the relation and the domain, the relation and the function space, where the function acts and where the relation acts, or how the relations are matching each other. And we talked about the domain, range, and codomain spaces. And that's all we need to know for the basics of mathematics for now. We'll come to set theory and number theory and everything else like that. And with your help, together we can build a stronger foundation for future mathematicians, scientists, engineers, and other businessmen. This is all for today. Thank you. Like, share, and subscribe by Imperium Engineering. Have a great day.